channel. So today we will discuss on capacitor part 3. I would recommend part 1 and part 2 before watching this, where the link is in the description box. The most widely used capacitors are parallel plate capacitors. Today's section we will discuss how to derive the equivalent capacitance for a parallel plate capacitor with and without dielectric. Now what is meant by a dielectric? In insulators, electron remains attached to the atoms or molecules. However, these electrons are subjected to small movements under the influence of external electric field. These microscopic movements give rise to some important electrical properties, and in account of that electrical properties, we can call insulators as dielectrics. Dielectrics are essentially an insulators. It can be polarized by allowing a small displacement to its charges. Dielectrics are of two types, polar dielectric and non-polar dielectrics. The dielectrics which is made up of polar molecules are known as polar dielectric. Now what is meant by a polar molecule? A molecule in which the center of mass of positive ion is not coinciding with the center of mass of negative ion. Such molecules are known as polar molecules.
The polar molecules have unsymmetrical shapes. They have permanent dipole moments of the order of 10 power minus 30 coulomb meter. For example, a water molecule has a bend shape with its two OH bonds inclined at an angle of 105 degree as shown in the figure. It has a very large dipole moment of 6.1 into 10 power minus 30 coulomb meter. Some other polar molecules are HCl, NH3, CO, CH3OH, etc.
The dielectrics made up of non-polar molecules are known as non-polar dielectrics. In a nonpolar molecule, the center of mass of positive ion coincide with the center of mass of negative ion.
Examples for nonpolar molecules are hydrogen, nitrogen, oxygen, carbon dioxide, methane, etc. As shown in the figure, these nonpolar molecules have symmetrical shapes.
Polarization of a nonpolar molecule. In the absence of an external electric field, the positive ion of the nonpolar molecule coincide with the center of mass of the negative ion. The net dipole moment will be zero. But in the presence of an external electric field, the positive ion gets polarized or gets displaced in the direction of the external electric field, and negative ion gets displaced in the opposite direction of the external electric field. And this displacement of charges continues till the external electric field is equal to the internal electric field. Thus, an induced dipole moment will be there in the case of a non-polar dielectric or a non-polar molecule.
Here is a figure of a non-polar dielectric in an external electric field. The induced dipole moments of different molecules add up, giving a net dipole moment into the dielectric in the direction of external field, as shown in the figure.
Polarization of a polar dielectric. In the absence of external electric field, the polar dielectric will have a permanent dipole moment. And this polar dielectric or polar molecules align randomly due to the thermal agitations. But in the external electric field, these polar molecules or these dipoles aligns in the direction of the external electric field, and thus there will be a dipole moment in the direction of the external electric field.
The figure shows the polarization of a polar dielectric in an external electric field. When an external electric field is applied, the dipole moments of different molecules tends to align with the field. As a result, there is a net dipole moment in the direction of the field as shown in the figure.
Hence, both polar and non-polar dielectric will have a net dipole moment in the presence of an external electric field, and this fact is known as polarization of dielectric. Polarization is defined as the dipole moment per unit volume, and its magnitude is equal to or referred to as polarization density. When a dielectric is kept in an external electric field, it undergoes polarization. Due to this polarization, there will be induced charges on the dielectric, and that induced charges will set up an electric field inside the dielectric which is opposite to the external electric field. That electric field due to the polarization is denoted by EP, which is opposite to the external electric field E0. So EP is the electric field due to the polarization, E0 is the external electric field. Due to this, the original electric field inside the dielectric, that is E, is the electric field inside the dielectric get reduces to E0 minus EP, where E will be in the direction of E0. Now comes to the dielectric constant. Dielectric constant is denoted by the letter K. It is the ratio of the original or the external electric field to the electric field inside the dielectric. So K is equal to E0 divided by E0 minus EP, where E0 is the external electric field and E0 minus EP is the electric field inside the dielectric. Capacitance of a parallel plate capacitor without dielectric. So in order to find the expression for the capacitance, here I am considering a parallel plate capacitor where the upper plate is positive charged and this lower plate is negative charged. Let the thickness of the capacitor plate be small d. Let A be the area of the plate. Definitely, according to the Gauss theorem, there will be an electric field existing in between the plates. And that electric field E is equal to sigma divided by epsilon 0, where sigma is the surface charge density. Here, sigma can be replaced as Q divided by A. So, the equation for electric field E becomes Q divided by A epsilon 0, where Q is the charge and A is the area of the plate. Now, since there is an electric field, definitely there will be a potential difference between the plate. And the equation for potential difference is equal to E into the distance d. Electric field into thickness. Instead of electric field, I can write the equation Q by A epsilon 0 into d. The equation for capacitance. C is equal to Q divided by V, which is equal to Q divided by. We got our equation for V, that is Q divided by A epsilon 0 into D. This equation can be substituted in the equation of capacitance. So instead of V, we can write it as Q by A epsilon 0 D, where Q and Q cancels and the final equation C is equal to epsilon 0 A divided by D. This is the expression for capacitance of a parallel plate capacitor without any dielectric. Here, the capacitance only depends upon the nature of the material, that is the permittivity, area of the plate and the thickness of the plate. Plate capacitor with dielectric. So here we will derive an expression for the capacitance of a parallel plate capacitor when you are inserting a dielectric in between the plates of the capacitor. So here is a parallel plate capacitor where you are inserting a dielectric of thickness T in between the capacitor. Now without dielectric, the capacitance Z0 is equal to epsilon 0 A divided by D as per the previous derivation, and the electric field in the region between the capacitance E0 is equal to sigma divided by epsilon 0, which is equal to Q divided by A epsilon 0. Now, when the dielectric is kept in an external electric field, it undergoes polarization. As a result, there will be an electric field within the dielectric. So, the total potential differences, when you are considering this figure, the total potential differences arises due to two electric fields. One electric field is due to the electric field inside the dielectric, and other electric field is the E0, that is the external electric field in between the parallel plate capacitor. So the total potential difference V will be equal to E into T plus E0 into d minus t, where E is the electric field in the dielectric, T is the thickness of the dielectric, plus E0 is the electric field in between the region of the plates, and D minus T is the thickness of the capacitor plate. The total thickness was D. In that thickness, a T thickness dielectric was inserted. The remaining thickness is D minus T. Now, instead of E, I can write it as E0 divided by K into T plus E0 into D minus T, where E0 is the external electric field and K is the dielectric constant. So dielectric constant is the ratio of external electric field to the electric field inside the dielectric. So E can be replaced as E0 divided by K, where E0 is common here. E0 can be taken outside. So this equation becomes E0 into T divided by K plus D minus T. So we got an equation for potential. Our aim is to find an expression for the capacitance. Capacitance C is equal to Q divided by V, where Q is the charge and V is the potential. In this equation, instead of V, we can substitute E0 into T by K plus D minus T. So C becomes Q divided by E0 into T by K plus D minus T. So the equation for capacitance becomes Q divided by E0 into T by K plus D minus T, where E0 can be replaced as QA by epsilon 0. So the equation becomes C is equal to Q divided by QA by epsilon 0, Q by A epsilon 0 into T by K plus D minus T, where Q is common, it cancels, and the final equation becomes epsilon 0 A divided by T by K plus D minus T. So this is the general equation for capacitance with dielectric. Epsilon 0 A divided by T by K plus D minus T. Capacitance with dielectric C is equal to epsilon 0 A divided by T by K plus D minus T, where T is the thickness of the dielectric and D is the thickness of the capacitor plate. Now, suppose the thickness of the dielectric is equal to the thickness of the capacitor plate, that is D is equal to T. Here you are considering that D is equal to T. So, in this equation, in the equation for capacitance, T can be replaced as D. So, the above equation becomes C is equal to epsilon 0 A divided by T by K. Instead of T, substitute D. So, it is D by K plus D minus T. So, what is D minus T? D minus D, it becomes 0. So, it is 0. So, here C is equal to K into epsilon 0 A divided by D. Now, what is epsilon 0 A divided by D? It is nothing but C0. So, I can write C is equal to K into C0. Or, if you are inserting a dielectric of the same thickness of the capacitor, then the capacitance increases K times the capacitance without any dielectric. C is equal to K into C0, where K is the dielectric constant. Uses of capacitors. Capacitors have a lot of uses. It is used in almost all electric and electronic devices and circuits. So we will list out some of the uses of capacitors. The first one is that it is used to produce the desired pattern of electric field lines. In radio circuits, tuning is done with the help of capacitors. Then, in the power supply, the rectified output is smooth with the help of the capacitors. Capacitors not only store charges, but also it can store the energy in the electric field lines. There are a lot of other uses for the capacitors. It is an inevitable factor in all kind of electronic devices. That's the end of the session, capacitor. We will meet again with yet another important topic for your board exam. Thank you for watching me. Thank you and keep watching.